Hi everybody. Today we're going to start our first real lesson in physics. We're going to be taking a lot of measurements in science class this year, probably ones that you are used to, mass, length, time, volume, things that you've worked with in your previous science classes. But we're also going to talk about some measurements that are a little different. So we want to be able to look at those different types of measurements. We're going to differentiate between what are scalar measurements or quantities and vector measurements or quantities. So you might be asking yourself, well, what are they to begin with? Well, a scalar is a physical quantity or a measurement that has a magnitude or size only. That's a big fancy word, that magnitude, and we use it a lot. But if you just remember, it simply means the size of something or how big something is. Examples of some scalar quantities or measurements you already know include things like temperature, mass, time. These measurements do not need a direction in order to fully describe the measurement. The measurement simply on its own will tell you what it means. Vector quantities, on the other hand, are physical quantities or measurement that have both a size and a direction. So they have to have a direction in order to really describe the quantity. And as I told you, motion is the first thing that we start to talk about, and direction is really important in motion. Think about if you had, you told everybody in your class to come to your house after school, and you said you live 3 miles away. I doubt anybody would be able to get to your house. They know how far, but they don't know in what direction. So you would have to give them a little bit more information in order to fully describe how they can get to your house. Examples of vector quantities you may already know, as far as the words go, are things like velocity, force, momentum. And you may say, well, I already use those words in my everyday language, and I don't worry about direction with them. Well, we have to think about these words in science terms. So when we do use them in class, they have maybe slightly different meanings than the words that you interchange them with. So for example, you might think of velocity as being somewhat equivalent to speed. Speed is the size of the velocity. It tells us how fast we go. When you look down at your speedometer when you're driving either to or from school, your speedometer tells you just how fast you're going, but it doesn't tell you whether you're going from home to school or school to home. So when you know that you are going a certain speed on your speedometer and going from school to home, now you have a velocity because you have both a size and a direction. So vectors require a direction in order to be included in order to fully describe the measurement. Here are some examples, and let's just check and make sure that you can categorize them as either a scalar or a vector. If you want to try this on your own, pause the video for a couple seconds, jot down what you think they are, and then we'll review. All right, let's look at the first one. The first one is 5 meters. It's a measurement of distance, but it doesn't tell us a direction. So as a result, he is a scalar. Our second one now, we have 5 miles, a distance, but it tells us north. So we have a size, how big our length is, 5 miles, and we have a direction. He's a vector. Temperature, 320 degrees Fahrenheit. It's a size. Whether or not we need to know direction and temperature doesn't help us at all, because we would know that anything less than 320 degrees would be cooler, anything greater than 320 degrees would be hotter. So there's no real direction even necessary in temperature, and as a result, they are scalars. Time. Time always clicks forward. We know the direction time moves, so we don't have to ever give a direction in time. Hopefully you recognize this 48 milliseconds as a time measurement, getting a little bit used to some of those prefixes. So these are scalars. 5 feet to the left. Sometimes our direction doesn't have to be north, south, east, west. It doesn't have to be actually what you think of as directions, but instead it gives information relative to another place or position. So at least it tells you, are you going 5 feet to the left of the table, 5 feet to the left of the other person, 5 feet to the left of your current position. You're essentially giving a direction along with the measurement. So that is a vector. Here's a speed, 55 miles per hour, just tells us how fast. Doesn't tell us where we're going though. That guy is a scalar. 32 feet per second down. And again, just like the one up here on to the left, up, down, that's considered direction. You know how fast and in which direction. That guy is a vector. And our 23.6 kilograms. Mass, if it gets bigger, it's greater than. If it gets less, it's less than. We don't need direction in order to fully describe something's mass. So that guy is a scalar. Hopefully you got through that okay. So now how do we represent vectors? Vectors are drawn using arrows, right? So we have an arrow here, and if you look at it, the arrow that the arrow that does not have the tip is considered the tail. The part of the arrow that has the pointy tip, the pointy part, is considered the tip. When you draw vectors, they're drawn to scale and in direction of the vector. So if you look at these two vectors here, they're both going in the same direction, but one is bigger than the other. So whatever measurement this is measuring, it's actually a larger measurement in size than this one. When we draw them to scale, think of them like blueprints or maps. You have a certain key. 1/4 inch represents a mile, something like that. And that's how we draw vectors when we draw them as scale diagrams. Vectors are considered equal if and only if they have the same size and direction. They don't have to have the same starting and stopping position. They just have to have the same size and the same direction. And that becomes important when we want to do some manipulation with vectors and we want to be able to move them around. So let's look at some examples. This first set here, same size, same direction. These guys are equal. These two here, let's look at the direction of which they're going. The arrow tip in this one's pointing this way. The arrow tip in this one's pointing that way. So even though they look like the same size, they're not in the same direction. So these vectors are not equal. These two vectors here, again, they look like they're the same size. They're pointing in the same direction. These guys are equal. And last, these two. Again, look like the same size, but this one's pointing up and to the left. This one's pointing up and to the right. So as a result, the direction's not the same. These guys are not equal. Very important to make sure that we have to have both size and direction in order to make sure that vectors are equal. Now, how do we manipulate vectors? We're going to learn about this more in class, but what I want you to understand is vectors are not like your normal measurements that are the scalars. You just can't add them together and come up with an answer, right? If you had two things that you put on a balance, one was 20 kilograms, one was 40 kilograms. If you wanted to find the total mass, you would just add them together. Not that simple with vectors. So we need to learn some ways in order to manipulate them and add them together or subtract them or do those things that we do with a lot of different measurements, but we do it in a special way with vectors. When you do add or subtract vectors, you call that the resultant. It's the result of adding or subtracting the vectors. We're going to learn two methods in class. We're going to learn first the graphical method, and that's going to be using those scale drawings, the way we can find out the resultant and add them together by drawing those arrows to scale in the direction they go. Hopefully you will realize afterwards that that's not always the best thing to be able to do. Once we understand vectors and how we can manipulate them, we're going to learn a little bit of an easier method that's called the resolution or component method. And that's where we're going to use those right triangles and trig rules that you learned about so that we can maybe come up with a different way so that we don't have to always take out a pencil, a piece of graph paper, a ruler, and a protractor to draw all these vectors to scale in order to do just some math with them. So both of these methods we will address in class. We will do the graphical method again just to make sure that we understand what we are doing and why we are doing it. But then once we're really good at that, we're going to move on to that resolution or component method, and we're going to stick with that for the rest of the year. So if you have any problems with the trig, please come and see me, because that's what we're going to use to be able to do any type of math with those vector quantities that we're going to work with.